Okay, so you're gonna definitely want to make notes on here about things that I go over, especially on this front side. I said I'd kind of be reteaching it. That's what I'm doing right now. On this first part here, we're dealing with different substances. And so in case you don't remember, we start by breaking these down into one of two categories. We can either have pure substances or we can have mixtures. Okay. Now, in order to understand what this means is we have to be able to determine the difference between atoms and particles. All right, so particles, it really means like pieces. It doesn't matter if it's an individual circle like this, that's a piece, okay? Or maybe they're stuck together, that's still one piece, okay? Atoms are the individual parts. So each individual circle or dot or whatever you want to call it is an atom, and each piece is a particle, okay? Whether it's one thing by itself or it's stuck to other things, whatever, each piece is a particle. So the difference between pure substances and mixtures is that pure substances only have one type of particle. So if I wanted to label these up here as pure or mixture, this thing here just has one piece, one big piece. I would call that pure. This one has some pieces are two white dots stuck together. Some pieces are a black dot and a white dot. I would call that a mixture. The third one, again, is just one big piece. Call that pure. This one, all three pieces are the same. So there's only one type of piece. So I would call that pure. Letter E, there's different types of pieces. I would call that a mixture. And the last one, all the pieces are the same. I would call that pure. All right. So once we have that done, that's our first way of dividing. Now we can actually go further and classify the difference between elements and compounds. So at this stage, we know all the pieces in the sample are going to be the same. So now what we're going to do is we're going to look at those individual pieces. If there's only one type of atom, then it's going to be an element. If it's more than one type of element, or more than one type of atom, then that's going to be a compound. Okay? So I'm just going to look at the pure substances now, not the mixtures. This, I have white atoms, I have black atoms. I would call this a compound. Okay, B is a mixture, so I can skip that. Here, they're all black dots. I would call that an element. D is a pure substance, but if I look at each piece, they have a white dot and a black dot, so more than one type of atom. I would call that a compound. E is a mixture, so I can skip that. And what is F? Element. They're all the same, right? If I look at a particle, three white dots, just white dots, I would call that an element. Yep. So at this step, once we're dividing up the pure substances, you're just looking at the individual pieces and saying what's in it. Is it just one type of atom, or is it more than one type of atom? So for A, the answer should have been B and E. And for number 2, should have been A and D. And C should have been C and F. D, pure substances, so that would be A, C, D, and F. And for solids, we're just going to look at these pieces that are all arranged nice and orderly, close together like this, these cubes. So for that, I'd put A and C. Okay. All right. Can I erase all that? Are you still writing? All right, number 2, we're just going to look at this sample over there. How many singular atoms do you see in that sample? 0? Oops. How many molecules of an element do you see? 4? This, and this? All right, how many molecules of a compound do you see? Compounds would be this, and this. All right, how many total atoms do we have? So atoms in this would be 1, 2, 3, 4, 5, 6 here, 2 here. They're kind of all divided up the same way. So 6 here, 2 here, 6 here, 2 here, 6 here, 2 here. Should add up to 32. Okay, number of particles. So how many pieces do I have in there? 8. 1 piece, 2 piece, 3 piece, 4 piece, 5 piece, 6 piece, 7 piece, 8 piece. Is this sample pure or a mixture? It's a mixture because I have more than one type of particle. All right, number 3, what are the differences between a physical change and a chemical change? In a physical change, what's that? You can apply heat, but you could do that with both changes, really. Physical change, what this means is your starting substance is still going to be the same stuff at the end. This is just when you change like the size of it or the shape of something. It's a change in size, shape, or even phase. Those phase changes. So like if I have liquid water and I boil it and it turns into water vapor, the particles are still going to be H2O. So it's still the same stuff. All right? If I freeze water, it's going to be ice, but it's still going to be H2O. So I'm not making anything new. So I'll just put a couple of the phase changes on there. I could have put condensing and melting as well. Okay? Now, with a chemical change, we are actually going to make something new. A new substance. All right. So give 3 examples of chemical changes and explain why they are a chemical change. This could be any number of things. Could I put boiling or freezing something? Because we just said that's a physical change, right? We might say something like burning something. If you give any kind of examples where you burn something, that's going to be a combustion reaction. If you said anything like rusting, some of the pieces of evidence for chemical change would be a release of energy, gas bubbles produced. I don't know how many people did this I think everybody saw this last semester, like Alka-Seltzer in water. Okay. A color change, and I don't just mean painting something. That's not a chemical change. And then precipitate formed. And what that means is if you take two clear liquids, say, this is an example, take two clear liquids and you combine them and a solid forms within them. You're making something new there. That's another piece of evidence for a chemical change. Okay, so can I erase that? So for physical changes, could be any number of things. Any of the phase changes like boiling, melting, condensing, freezing, any of those. Changing the shape of something, a piece of paper, if you crumple it up into a ball, it's still going to be paper, but you change the shape of it, or tear it in half, tear it up into a bunch of little pieces. But the main idea is that whatever you started with, however you changed it, it's still the same substance at the end. All right. Number 6, some physical separation techniques. Okay. So one thing we can do is we can dissolve something. And what this is based on is a property called solubility. Okay. Solubility means that something can be dissolved in something else. So a lot of times we'll say salt or sugar is soluble in water. We can dissolve it in water. Okay. It's still going to be there though. There's still going to be sugar in water if you dissolve sugar in water. And you can tell because if you were to drink that water, it would taste like sugar water. All right. Another thing we can do is we can filter things. So we call that filtration. So we use some kind of filter that lets some particles through and not others. And so filtration is based on the size of the particles. So I'm putting this down because it's important to know like what method you would use of physical separation to separate two things. We could do something called distillation. Okay, distillation means we're relying on different boiling points. So it's based on the boiling points of the substances. So maybe if I dissolved some salt in water and I had salt water and I wanted to separate them back off, I could boil out the water because it has a lower boiling point than salt. And if all the water escapes into the air, all that's left behind is the salt, and therefore I have separated them. Another thing is if you've got magnetic materials, you could use a magnet. So based on magnetism, I mean, that's kind of self-explanatory. But an example of that would be something like iron is a magnetic material. When I was a kid, I had like a gravel pit behind my house. I used to go out there in the sand and take magnets and get iron. I don't know why. I was bored, I guess. Okay. Number 7. So all these things here, we can use all these to separate mixtures. All right, that's important to note that. All right. So if we just have a mixture, different types of particles, then we can use these physical separation techniques. If we've got elements, there's not a lot that we can do because, like Dalton said, you can't really, they're indivisible, right? We can't break them down into smaller parts. We could separate different elements, but if we had different elements together, that would actually be a mixture, right? So we're talking about compounds here. How can we separate compounds into their smaller parts? And so what this is called is a decomposition reaction. Okay. Splitting apart something, sometimes they'll call this using electricity, they call that electrolysis. All right, but really that's with, if you've got compounds, you can't just like boil them or filter them or do anything like that. You're trying to break them down into their individual pieces. And why that's so tough is because we have those chemical bonds holding the elements together, so we got to figure out some way to break the chemical bonds apart. All right, number 8. So with number 8, we got to understand what element symbols look like. Element symbols consist of one of two forms. Either one, they can just be a capital letter by itself, or they can be a capital letter followed by a lowercase letter. So basically, wherever you see a capital letter, that means that's the start of an element. So N here, that means that's the start of an element. Capital S here, that's the start of an element. So I have 2 different elements in this. One of them is capital N little a, and the other element is just capital S. What's that? It's asking how many different elements are present in this compound. So if I look at the formula, I can tell there's 2 because there's 2 capital letters. All right. On the next one, CaCl2, again, there's 2. And if I look at that, I see 2 capital letters. How many capital letters on the third one? Yeah, 3 of them. Now, we did a lot of work with ratios this semester so far, and we write them like fractions, right? Now, you could still write them as fractions, but it would get a little confusing when you get to the third one. So another way you might see a ratio written is like this. If I wanted to say the amount of sodium, the ratio of sodium to sulfur, I could do this. Na colon S, like that. And then this 2 after Na means that there's 2 sodiums. So I would put 2 for Na. And then what number do we have after S? Nothing there, right? So what does that mean? 1. So that would be a 2-to-1 ratio. On the second one, there's how many CAs? Just 1 because there's nothing after it. And how many CLs? So that would be a 1-to-2 ratio. And on the third one, I've got 3 elements. So what I can do here is I can look at the first element, H. There are 3 of them, dot, dot. And then there's P, capital P with nothing behind it. So there would just be 1, dot, dot, and then 4. Yep, 4 for oxygen. So that would be a 3-to-1-to-4 ratio. Okay, good with that? Okay, so I was talking about decomposition, and that's what they're doing here in this example. And you can look at this as different tests that they do, or it's just the process, what's happening, and they're marking it at certain points, comparing the two things. So we've got oxygen here, and we have sulfur here. And I see at the first step, zero point 0.3 milliliters of sulfur has been decomposed or been produced, oxygen 1.2 milliliters. All you have to do is compare these amounts. And if I do that, I can see that the left side over here is producing 4 times as much oxygen. So what was the formula of the original compound? There must have been 4 times as much oxygen, right? So I would say O4S. Or order at this point doesn't really matter. SO4, either way. So that's the formula. And write it for every statement. I always like to start with the one that is just 1 if possible. So that means for every 1 or for every S sulfur atom, comma, there are 4 oxygen atoms. Okay, so this is something that hasn't been talked about since last semester, doing a couple different tests for hydrogen and oxygen. So the first one is oxygen. The way you test for oxygen is by using a glowing splint. And so if you've got a sample that you think is oxygen, what you can do is you can burn a wood splint. You can blow it out so it's just glowing now, glowing orange. All right, but it's still glowing. If you put that into a sample of pure oxygen, it's going to light back up. Okay, so it'll burn. It'll go back to burning. That's the oxygen test. Because if you take, so the question is back on number 9, if you compare these numbers here, you'll see that each step, this is 4 times greater, like 1.2 divided by 3 would equal 4. Second step, 2.0 divided by 0.5 would equal 4. 3.6 divided by 0.9 equals 4. So the left side is always 4 times greater. All right, so number 10, the hydrogen test. If you're testing for hydrogen, you're actually going to use a burning splint. Pops. So if I take a burning splint and I put it in hydrogen, there's going to be a little explosion, a little pop. It'll go out. All right, and then we're on to number 11, the new stuff. So 11, what is a diatomic element? Okay, so this is elements that actually exist as two atoms stuck together. So a lot of times we might see dots and say, hey, that's just an element. It's just one thing. Hey, this is just a green element. Hey, this is just a red element. But there are certain elements that don't exist as just one atom. They're actually two atoms stuck together, like H2 or O2 or Cl2 or F2 or N2 or Br2 or I2 or N2. Avogadro's hypothesis, two gases of equal volumes at the same temperature and pressure will have an equal number of particles. Okay, and then Dalton's atomic theory, four main ideas from that: all matter made of atoms, atoms are indivisible, atoms combine to form compounds. When we do that, we rearrange the atoms. This is a chemical reaction. Okay, number 14. 14, I didn't like this question at all because when we did percent composition, we were talking about one compound and we were talking about the law of definite proportion, which means a compound will always have the same percent composition. I didn't really use percent composition at all. Well, I mean, I guess we kind of did in comparing separate compounds, but it gets, when we think of the percentages, actual percentages, we just use that for law of definite proportions. When we did multiple proportions, we were comparing different compounds and we were looking at the mass ratios. So I don't like trying to combine them in this question when we're talking about percent composition. All right. Okay, so 15, this is what I was talking about with percentages. First of all, we're going to express as fractions the ratio of the masses, and B, we're going to calculate the percent composition. So like I told you before, anytime you have to do percent composition, we have to figure out what is the total first. So in this, it says we have a 41.2 gram sample, so that's going to be our total right there. So if I want to do fractions for each part, okay, so we've got 24.72 grams of carbon. So I would do 24.72 grams of carbon over 41.2 grams. So that would be for carbon. The hydrogen is going to be 5.48 grams, because that's that part. Put that over 41.2. And then the oxygen, it says out of those 41.2 grams, 10.99 grams is oxygen. So I do 10.99 grams divided by 41.2. So there are my fractions. All right. So if I want to turn those fractions, those ratios, into percentages, I'm just going to divide them. So on the first one, I'm going to take 24.72 and divide by 41.2, and I should end up getting 0.6. All right, now that's not the percentage, that's the decimal. The percentage is if I multiply that by 100. So 0.6 would actually become 60%. So 60% of that 41.2 grams is carbon. Yeah, or move it two places. That's the same thing as multiplying by 100, right? So hydrogen should come out to be 0.133 or 13.3%. And oxygen should come out to be 0.2667. And if I make that a percent, that would be 26.67%. This stuff that they're talking about here is called propanol. Okay, that's the chemical, propanol, whatever that is. We don't really need to know what it is. But in C it says the chemist analyzes a sample of another compound. It's unknown. We don't know what it is. And he sees that it has this percent composition. I notice that all those numbers match up exactly with all these. So I am going to say, yes, this is propanol. The percent composition or something like that is the same. And this is according to the law of definite proportions. No matter how much propanol I have, propanol is always going to be 60% carbon, 13.3% hydrogen, and 26.67% oxygen. Always going to be that way, no matter how much I have. No matter if I have a milliliter or I have 1,000 liters, it's always going to be made up of the same things in the same proportions. All right, so when I see these types of problems where I've got two compounds, I know we're talking about that multiple proportions thing. And I said I didn't like the way that they put this as mass of S to mass of O. I wanted you to actually switch those around. So if your numbers are different from me here, it might be because you didn't switch them around. I like this so that we're always comparing them by putting the larger number on top, which if I look at these two compounds, the larger number out of the two things in it is oxygen. Okay? So if I did compound A right here, I would take 22.4 and divide by 19.6. That's the grams of oxygen over the grams of sulfur. Okay? And so that ratio would come out to be 1.14 or 1.14 to 1. B, if I divide that, so I would divide 144.6, divide that by 63.3, that would come out to be 2.28. Now, in these problems, we should be familiar with this, saying that when we find these two ratios, we're trying to find the relationship between them. So when we did that, we kind of took the larger number compared to the smaller one. Maybe just divide it and see what is the relationship there. And you see that 2.28 is twice as large, okay? B says, what do those above ratios tell you? Well, so like I said, A, really what this means is it means 1.14 grams of oxygen per 1 gram of sulfur. Because if you've just got a number, then that means the denominator is just 1. That's all. So 1.14 is the same thing as 1.14 over 1. So if I write so it means that there is 1 gram of sulfur for every 1.14 grams of oxygen. And in the compound B, there is 1 gram of sulfur for every 2.28 grams of oxygen. How does the mass ratio for compound A compare to that compound B? Compound B is twice as large or has 2 times as much oxygen. Right, for every statement for compound A, we pretty much already did right here. And so now we need to sketch these particles. So as far as sketching these, I'll just make a black dot be S, a white dot be O. And so for compound A, keep it simple, just 1-to-1 ratio of atoms. So just do, because I know this is the smaller one, so just do 1S and 1O. So that would be compound A. If I wanted to write the formula, I could, 1S and 1O. So, and then in B, I know that that ratio of oxygen, since that was the top element, that was the larger element, that's the one that's actually changing. So it's the oxygen that is twice as much. In both of those examples, the ratios, the sulfur was on the bottom. So that was going to be 1 each time. So in compound A, it was 1.14 to 1, talking about oxygen to sulfur. In compound B, it's 2.28. We're talking about oxygen over sulfur. So that's 2.28 to 1. So the thing that's changing is the oxygen, not the sulfur. So when I do this, I'm still going to keep the sulfur the same, but now I'm going to make twice as much oxygen by making 2 oxygen atoms. Maybe just put 1 on each side. And there you go. And 17, explain why we cannot separate by physical means a hydrogen atom from a water molecule. So a water molecule, H2O, this is a compound. It's held together by chemical bonds. We cannot separate compounds by physical separation techniques. The only way we can break H2O down is by decomposing it, which is a chemical separation technique. All right? Can't just filter it. Can't filter water and have the H2O come out. You can't boil water and have just the H2O or H2 leave. All right, so that's the end of the video finally.